Hi guys, thank you for coming to the OLED Web channel. We are a channel that focuses on reading the latest archived works on NLP. Today, we're going to be reviewing a classical NLP paper, which is also the paper behind the famous GPT-3. The paper's title is Language Models Are Few-Shot Learners. But today, I will just go over um, the first two sections of the paper, which are introduction and approach. But I think I would go through this paper very slow because I myself benefit a lot from reading this work. Even I am kind of an experienced researcher in speech. I think lots of you are beginners in doing research. I do recommend you to read carefully or read every sentence of this paper and try to understand why the author said that and what does the specific figure mean and what does this analysis show the thinking of the authors. All right. I think I would first start with the abstract. And you can see that this is a paper which was published about almost 2.5 years ago. At that time, even before the GPT-3, there are already some works that's focusing on zero-shot learning. But at that time, fine-tuning on a specific task is very popular for NLP. And when there is a task-agnostic, because if you're training a prediction model which is supposed to be task-agnostic, and suppose you wanna focusing on or testing on a specific task, you would need some task-specific dataset for your fine-tuning, which is known to all of us. And interestingly, this is the most popular NLP approach in NLP, especially in industry. I've seen lots of cases that when somebody got a new task, what basically they were doing is that they downloaded or they start with a very large pre-trained language model, then they collected lots of in-domain or task-specific task data, then they work on the fine-tune. This works, but in this paper, these authors are focusing on the zero-shot and a few-shot cases, in which when given a specific task, you do not have a lots of training samples. Because why? Because the author mentioned that although as is known to all of us, scaling up, making a larger language model does improve the task agnostic performance. And especially they have shown that in their few-shot learning, they have reached the competitiveness with the prior state-of-art fine-tuning approaches. I think that this writing is very delicate. I recommend you to pause the video and think about what does the author mean here. Well, this is a nice way of saying that they are not better than the state-of-art algorithm, but they're saying that they're very close, and that they're saying their algorithms are promising. They recommend people to try this. That's the writing of reaching competitiveness mean. Okay. So I think GPT-3 or the model used in this paper would be used without any fine tuning, which is the point of zero shot or few shot. And I think this might look familiar to you. It said the GPT-3 can generate samples that is related to nowadays fairly popular usage of GPT, which is Chat GPT, right? The GPT model is being used in the text generation task. And also, I think the Dolly thing. Not talk about that. All right. I think we finished the abstract. Let's move on to the introduction. So they first talk about the history. Back in 2013-14, I think Stanford people invented or introduced something called a word-to-vec. Some people are still using that. Okay. It basically, the point is that you can, for the word king, you can map the word king into a feature space. Suppose this is a two-dimensional feature space, and this is a vector of king. Okay. In the following, I won't draw the vector, but just a draw dot on the hyperplane. And you can have convert the word queen into another vector. Okay. And also you can have a word man and a word woman. And the interesting thing I remember was that the authors, they demonstrate that when they have this vector king minus vector queen, they're going to be able to get this vector. But this vector is very similar in terms of a mean square error or some kind of a measure compared to the vector man minus vector woman. Interesting, right? And then later on, in the work they mentioned about here, people started to use RNN. That traces back to also, I think, the famous I think is probably the chief scientist in OpenAI now, but at that time he was a Google researcher, Jeff Hinton's student. Let me see. I kind of I think it's Su whatever, right? That's his name. Sorry, I cannot remember his last name. He's very famous. He had a very famous work on what do you call that? Sequence to sequence. Just Google the word sequence to sequence modeling. And the RNN means that they're capable of using the recursive neural network to unsupervisedly train a model which can generate multi-layers of representation. And it contains a contextual state, which means you remember that the example I gave you here is a single word. Although you can extend it to bag of words, you can get a what I call a bag of words vector. But in the RN case, the vector or the representation would be coming from all the history before the current word, right? So this contains richer contextual information, which they call it stronger. And later on, I think all of you know this is a transformer, okay? And probably BERT, yeah. I think they only put a transformer reference here, just transformer. Attention is all you need. By the way, I do have a paper reading on transformer. Just search attention is all you need or transformer in my channel. You can see that paper reading is actually from a speech researcher perspective, from a speech recognition perspective, because ASR people do use transformer at that time. Yeah, that's the history before coming to the large language model. But there are some limitation of the large supervised to have a large supervised training set, because I remember these models the author talked about are all supervised. That means they have a pair of input and output, right? They have the labeled X or Y, these type of things. But as we all know, point out that it is difficult to collect a large supervised training data set, which is also true in the speech recognition. Because I'm a speech researcher, as far as I know, it takes tons of money to collect 1 hour of transcribed speech. So this is why lots of small or mid-sized companies, they do not have training set more than dozens of thousands of hours, which limited their capability of competing with the super large companies. But as we know that later on people have the unsupervised training, so you can train a very, very large model without need to have people labeling the data, which is called self-supervised training or pre-training. So that's the first limitation of the models before the GPT-3, okay, or unsupervised model. The second limitation was that the potential to exploit spurious correlation in training data. The meaning of a spurious correlation means fake causality, fake correlation. Or suppose John would go to work every weekday, but he saw a red car passing in front of his house every Monday morning, every weekday morning. But is there a correlation between this? So can we safely assume that John would also see that red car during weekends or next week? You can't, right? So this is called like a spurious correlation. And because you collect the training pairs of X and Y, so your model is very likely to learn this type of fake correlation. So then model make a wrong predictions. What does the expressiveness of the model? You can just Google it by yourself, but I give you a quick explanation. That means what type of computation a model can perform. Because right now, most of the models are deep neural networks. When I say deep neural networks, I mean deep neural networks. That doesn't mean DNN or this vanilla DNN, okay? So for DNN, the expressive the model, let's call that using E, okay? If we can measure that, it's proportional to the exponential to the number of layers. So you can see that when for the DNA model, the more deeper the model is, the more expressive the model is, which means that the model is capable of computing very complicated questions, very sophisticated or complex computation. Okay, narrowness of the training distribution. It's easier to understand. You remember that we have training set and testing set. So when the training distribution is the training set, you happen to do not have a wide coverage on the true distribution. Okay, then you'll be limited to your data. Okay, then the model doesn't reflect the true distribution of the data or the testing distribution. Then you will have an issue. Yeah, lots of people say that I think you have seen lots of wrong saying that. Okay, for instance, I say, well, if you can get a larger model, that means you have a better capability of modeling your data. Okay, or modeling. I would agree it might model your training data better, but that does not necessarily in the author's word does not necessarily generalize better auto distribution, or say it does not necessarily generate a model which is good for your task. Okay. And you can say, okay, well, I just try to see if I can collect more in-domain data or include those auto distribution data into it. Okay, well, I mean, this is a philosophy issue. Think about autonomous driving. Okay, take the object detection in autonomous driving, for example. You can just incorporate more and more road data, the real world data into the model training set. Okay, but every day there's going to be new scenario. How do you handle these type of emerging out of distribution cases every day, right? Doesn't mean that with the current existing data you make your model larger. Well, that won't solve your out of distribution problem. Get it? That's what it meant. And this, I think they also point out the one issue of fine-tuning models on specific benchmark. And you know that there are some super glue, QA, comprehension, whatever NLP task you may name it. There are probably dozens of evaluation out there. But the thing is, suppose you use your fine-tuned models on specific benchmark, that may exaggerate the actual performance. So take the speech recognition, for example. I think most of you would probably have heard of a LibreSpeech task if you have subscribed my channel. LibreSpeech task. This is a reading speech recognition task, and I think right now the state of art WER is less than 1.8%, less than 2%. But as we all know that, regardless of the dictation or spontaneous or conversational speech, let's just talk about the reading speech. Definitely for human, it's definitely about 5% most of the time. Okay, even for the reading speech, because the accent, the noise issue, would definitely, make the WER to be about 5% most of the time. I won't say it would be about 5% all the time, okay? So this is in the speech recognition domain, when people are keeping fine-tuning their models on one specific task, may give others a wrong impression that this problem has been resolved, but actually it's not. What they have achieved was only a very fine-tuned model on specific benchmark. Makes sense? But I didn't say that fine-tuning on the libre speech was meaningless, because that's also important to test out what's the better model architecture or neural network architecture to model the data in the libre speech dataset. So it's meaningful for algorithm and algorithm to be compared together in that libre speech. Okay. And here the author talked about their proposal method or something they want to do is that seamlessly mix together or switch between many tasks and skills. What they actually meant was, remember that for the current NLP models, one model can only do one thing, okay? Most of the thing was like this. If it's before the GPT, okay, ZeroShot model, they're all task-specific model. If you are using a QA model, you have to feed the model with questions. But if you're switching to NER, name entity recognition, you cannot send a question into the NER, okay? Then you will get a very bizarre results. But like our human being, we're capable of, fluently or seamlessly switching between the tasks very naturally. So this is also something they want to achieve. And they talked about the meta-learning. I think meta-learning is not very popular now. It was very popular, I think, maybe 1.5 years ago. Meta-learning, I think, is still supervised learning. But the meta-learning is all about condition on the natural language instruction and or field demonstration of the task. So they also mentioned that I think before their paper, before the OpenAI's GPT got popular, there are some other paper they mentioned their paper as ZeroShot Transfer, but actually they were not, because in OpenAI people's definition or in a common sense definition, whenever you mention the word zero shot, that means no gradient updates are performed. So you're not supposed to update your model, okay? So it only involves providing a inference time demonstration. So in a short word, only in the testing, I give you no example, okay? You just tell me for this new task, this sample, what's your predicted output or what's your outcome of your neural network model. And also, so I think the author they talk about it's better to use the in-context learning to refer the inner loop of meta-learning. So what does the inner loop of meta-learning in this work? I think the author they use the figure 1.1 to illustrate this. So they have an outer loop, like say, remember the for loop? This is the outer loop, okay? Outer loop. And then you have this type of inner loop. Make sense? So this one is addition, but the context was addition, right? But this context is letter sequence scrambling, and this context was the synonyms, okay? But as you can see that the meta-learning does not train 3 separated models. Instead, they train just one model, one unified model, but with the contextual information. So at the inference stage, they are just saying, okay, we can just tell our model either the task we're performing or give it a prompt or hint, so the model know what the context is and they can perform the in-context inference. Okay, I think the meeting will end in 10 minutes. Do you want to discuss? Do you have any questions? Let me see if somebody's online. Okay, let me see if I can. It seems that you're all leaving. Okay, I will continue. I think the reason why, that's my understanding. Feel free to correct me if I were wrong. The reason the meta-learning was no longer popular nowadays was actually its performance, because the results, you can see that it has a very bad result. And I know for the ASR, some people did play with meta-learning, but you know, it doesn't work if you want to combine the read speech with dictation task, right? Or spontaneous speech. So I don't know why it didn't work, but it just doesn't work. And also, lately, I think the author, they talk about if you are just increasing the model parameter, the meta-learning get better. That's what it meant. But it's still behind the sorter system a lot. Remember, these sorter systems are fine-tuned on specific tasks other than using one unified model for everything. Okay, then we got GPT. They finally talk about GPT on page 5. This is the first time they talk about GPT-3. Okay, yeah, as we all know that, everybody knows that nowadays, this magical number 175B. 175B. And it's don't remember that. Don't forget that. It's autoregressive. Remember, it's always either from, is always how do you say that? From left to right. Left to right. So given a history of n words, what's the next word? Okay. So you may say it's not from right to left. So this is why when you play with ChatGPT, you can see that the ChatGPT's interface is keeping popping out words or letters or code. So this is left to right. And you can stop anytime. Remember, it has a button which says stop generation. So that's you can stop the autoregressive process anytime you want. They talk about 3 conditions. I think it might be new back in 2020, but now it's 2023. Everybody should be very familiar with few shot, one shot, zero shot. But let me explain this very quickly, okay? I think the author talk about here. Cannot see that clearly. So first of all, before I explain the zero shot, one shot, few shot, let's look at the traditional fine tuning. Suppose you're given 3 examples. Oh no, n examples. And suppose you have a base model already, or base backbone model already, and you want to fine-tune this task-agnostic model to the task-specific model. Then basically what you do is that you see this is a pair of input and output. And you send this into the model, and it's called training, right? You got a gradient update. Because you see sending the C order, you can get output, right? You can get output of Y star. Then you compare the Y and Y star in a C loss or whatever loss or NL loss. You get an error. Once you get the error, you can get a gradient, right? You use a gradient update, you update your model. But this case, this batch only has 1 sample. But this is an illustration purpose, okay? You update your model, and then you met the next example, you do the same thing, you update your model. Then you keep doing this until you finish updating the model with all the fine-tuned datasets. Fine-tuned dataset. Then, in the testing or inference stage, you're given one X. And what is Y? What's the output? That's a traditional fine-tuning. I would. So what is zero shot? Zero shot means that no gradient update are performed as shown in the right figure. You have a GPT-3 model, and all you have is X. Send X to it. That's it. That's it. Whatever Y you get, that's it. You may say, okay, wait, the GPT-3 model is not. It's not what? It's not task specific model. You're right. So this is why most of the time zero shot model would get a very, very worse result. Very, very bad result. But you can definitely do one shot learning. So give the model an example. So this time the input to the model is what? This. So the whole thing going from here to here is input X. And the model is expected to output Y. So you can see the only difference between the zero shot and the one shot was the example. So sometimes we also call the example prompt. I'm sorry, it should may not be called prompt. It might be something else. I don't know whether this can be called prompt or not. I'm a little bit confused here. I think you may call this hint or prompt. I think it's type of prompt. I think okay. I think this can be called prompt. This, I mean the example. So you can see this time I think the model would definitely see if you can get something from the example or the prompt I talk about, okay? To see if you can, oh, this is a pattern. I should generate the Y given X, right? So you can imagine that, but let me ask you a question. What the training should be? Of course, yeah, the training is not changed. So the model you train for the one shot is the same as the model you train for zero shot. But that's my understanding. During the training stage, you somewhat have this type of prompted input, and then the system knows how to generate the output based on the prompt you give into the system. And this is, I think, how the one-shot thing works. Makes sense? And the few shot is an extension from the one shot. You just have more examples. You just have more examples sending into the model. So everything is got input into the model, and they expect you to have Y. So in this case, I think the system was more how to learn. More, I would say, using the paper's word, I think it's called in context learning. In context, this is called in context learning. I think this, if you talk about in context learning, that's meta learning, okay? But GPT or zero shot inference does not do learning at all, because there's no reference, no gradient update involved. So this is like an in context inference. Makes sense? I do want to talk about this figure 1.2. He also used the word particular striking. I think it's striking to me too. Pause the video if you can take a look at yourself and see if that's striking to you. Basically, this figure tells you two things. First of all, x-axis is the number of examples, okay? This is 1 example, this is 10 example, this is 100 example, probably 100. And this is accuracy. The higher the better. Model is better. And you can see this corresponds to zero shot, this corresponds to one shot, and this region corresponds to few shot. Okay. And the solid line all represent with prompt. Okay. And the dotted line all represent the no prompt. But you can see that with prompt or without prompt, especially you can see that when the model parameter got increased by 1 magnitude from 1.3 to 13 billion parameters, you can see you only increased from like a 5% to about 25. But if you increase the 1 more magnitude of the model size, you get almost 65. This is the first thing that is a particular striking. See, this is 1 magnitude larger, right? You only got 20% improvement. But this time you got 40% improvement. This is huge. And I mean, 25% is almost like a very, very bad system, if you agree with me. But 65, I wouldn't say it's good, but it's okay system. The second shocking thing, or striking thing, is the prompt versus no prompt. You can see when the model size are small, having prompt or have not prompt doesn't make much difference under zero shot, one shot, or the few shot case. But if your model size got really large, like 2 magnitude bigger than the original 1.3 billion parameters, which is 175 billion parameters, especially under the one-shot case, this improvement is huge. It improved from about 25% to about 45%. This is another 20% gain. Well, it also shows that for the few shot cases, there's not much difference. And for the zero shot case, it goes from zero to, it goes from nothing to almost 8%, which is also impressive to me. So if this is a 0% accuracy, that means the model is doing random guessing or not doing anything. But it's when you feed the model with a prompt, the zero shot inference is doing something. At least it's better. So doing something is a big gain from doing nothing, if you agree with me. So that's the two things that's particularly striking. They mentioned that here. So I recommend that whenever you saw the author use some type of special words, try to understand what they mean by saying this. Yeah. And they also talk about it broadly. They're saying that their model is capable of handling different NLP tasks like QA, test rapid adaptation. So for those of you who do not this, I would like to use a speech example to give you an idea, okay? It means you have a general model of ASR, but you want to recognize my voice. You can do something called online adaptation. So that means you have my voice being recognized constantly, but you update your model constantly, okay? And on the fly reasoning, I think that means you do not change the model parameter like their test rapid adaptation does, but you basically do some post processing based on, for example, you can leverage the knowledge base after you get the NLP results, some other external model, a second model, to manipulate the result from the first stage. That's my understanding. And then again, the GPT model, they can also do generation. I think they talk about the data contamination issue. So what is the data contamination? This is a growing problem when training high capacity model. So they use, for example, they use a common crawl dataset, but I think before them, or maybe somebody has done that, but most of people do not care much whether the common crawl dataset contains samples from the test set. But this is also the issue of using the large unsupervised model, because you gotta have to collect a lot of text from the internet. Even for our speech recognition, you do have to collect a lot of unlabeled recordings. But for example, for take the speech for example, does any of the recording in your unsupervised data set to be the same as the one that used in the test set? And some people argue that, okay, that doesn't matter, okay, because you do not have the transcription of the unlabeled recording in your training set. But I would view that differently, because you have seen the data, right? You definitely, for example, it's different, okay? Because it seems to me that it's equivalent. You have done some supervised adaptation to your model. If you just change your training, if you change your if you're arranging your data to make sure that this recording to be the last sample you use in the training, right? That means the model is updated to this special recording unsupervisedly. And then right after that, you use your model for testing. So that's not acceptable to me. Yeah, they have also done some updation studies. I think this is important. You cannot just have just one large model and tell, okay, this is working. That's not research, but you want to demonstrate people the process. How do you come up with this large model? I think, for instance, they show the size of the model. You see, this model size is very small, like 0.1 billion parameters. But you can see that they almost, this is a one magnitude, another magnitude, another magnitude, right? This is the process of getting there. Approach, I think this is, yes. Then we come to the second stage, which is approach. Okay. I think we have to talk about fine tuning, few shot, one shot, and zero shot. Okay. Model and architecture. It's similar as GPT-2. I don't think there's much difference between Transformer, GPT-2, and this stuff. But I don't think I'm gonna cover this today. But you can just imagine that it's a very, very deep model with proper self-attention, right? You see that? Yeah, it's layers of transformer, right? Might have slightly difference. Traditional transformer. They have heads. Okay. If you're using transformer, you have a self-attention. Okay. So I think if you're familiar with BERT, then you know how these models are trained. And I do have a sharing of BERT paper or model in my YouTube channel. You just search BERT, you can find my paper reading. I think this is similar to the training of the GPT-2 or GPT-3 model. The only thing different is that the GPT-3 model is way larger than the GPT-2 or the BERT model. I think the training dataset part is very interesting to me. Here they talk about how they downloaded and filter. They actually didn't talk about the details of how they filter this common crawl dataset, and how did they do the deduplication, and also this makes sense, right? They just put the Wikipedia, which I think is being considered as high quality data set. Because column crawl can be considered as a not very high quality data set because everything was from internet. There's no way of controlling it because the editor of the text might be somebody, might be anybody, but the Wikipedia has been modified. The text all written and closely examined by lots of people, right? You cannot just arbitrarily edit Wikipedia compared to common crawl. Well, this is interesting. Before filtering, they have 45 terabytes of compressed plain text. But after filtering, they only have 500 gigabytes. And they end up with 400 billion tokens. Well, I don't know what that means, okay? Seems a lot to me. But I believe that nowadays they have way more data than this because this is like 3.5 years ago. I think the ChatGPT or GPT 3.5, GPT-4. Yeah, they're talking about the training and testing set overlapping issue. Interesting thing that they have done the searching, but they were not able to do that because of bug. They definitely analyzed it. I think if you're a deep learning researcher, you might already know this, but if you're new to deep learning research, this sentence is very, very important. Just mark that. Very, very important. Large batch size and smaller learning rate. If you do not know why, I highly recommend you read these two papers. An interesting thing. This is a fun thing, okay? You can see 3 years ago, A100 and H100 GPUs are not available, but Microsoft was able to provide OpenAI with the latest GPU they have, and they build a high bandwidth cluster. You see that Microsoft supports OpenAI research a lot. Evaluation. I don't think there's much to talk about the evaluation because I'm gonna cover the results. They think should be addressed. So I'm gonna stop here. So for the next session, I would try to analyze the results section of the paper, which might take maybe two recordings. But I think nowadays, if you look at the GPT-3 paper, it does not have any fancy neural network models, and it doesn't have any sparkling mathematical equations. But I do think in this paper, it has fairly intriguing ideas embedded in it. And this is why it led to the success of ChatGPT. I'm going to try my best to see if I can analyze the results section as good as possible. Please stay tuned and subscribe our channel. Bye.